AVL trees. AVL tree is a balanced tree, a height balanced tree. It is proposed by Adelson, Welsky and Landis in 1962. The definition of an AVL tree is: an empty binary tree is an AVL tree if non-empty. The binary tree T is an AVL tree if it follows the following two conditions. A binary tree T can be called an AVL tree if TL and TR, where TL and TR are the left subtree and the right subtree of the tree, if they are AVL trees, and the height, the difference in the height of the left subtree and the right subtree is less than or equal to 1. So these are the two conditions. If these two conditions are satisfied, then a binary tree, a non-empty binary tree, can be called an AVL tree. Now the heights of the balance, the heights of the trees, or the height of each node can be found using a balancing factor. That is, you can say that an AVL tree is balanced by calculating the balancing factor for each node. So to calculate the balancing factor, this is the formula to calculate the balancing factor. Balancing factor of a node U is equal to height of the left subtree of U minus height of the right subtree of U. Now, and the value of the balancing factor of each node should be within 0, should be any of these three values. That is, it should be either 0, 1 or minus 1. Only then you can say that the tree is a balanced tree. So the balancing factor formula is obtained by subtracting the height of the left subtree of that particular node minus the height of the right subtree. And the value of the balancing factor should be either 0, 1 or minus 1. If it is any other value, then you can say that the tree is not balanced. Now let's see some examples of AVL trees. Now look at the first example. You have a tree, a binary tree, and the balancing factors of each nodes are given within brackets. Okay, now look at the first figure, figure A. Here you can see that the balancing factor of each node is 0, 1 or minus 1. That means this is an example for an AVL tree. Now look at the second example, that is figure B. Here the balancing factors are minus 1, 0 and 2. That means since 2 is not an acceptable value for balancing factor, you can say that this is an example for a non-AVL tree. Now look at this example, at the figure C. Here also you can see that it's a binary tree and the balancing factors of all the nodes are 0, 1 or minus 1. So this is an AVL tree, but look at the values of the nodes. Now the root node is D. In this figure, root node is D, and to the left of D you have a node with value B, which comes before D in alphabetical order. When you arrange the alphabets in alphabetical order, it comes before D, right? And the nodes to the right of D are the characters come after D in the alphabetical, when you arrange it in alphabetical order. That is, it follows the concept of binary search tree, where in a binary search tree the nodes to the left of a parent node should be a value less than the parent node, and the nodes to the right should have a value which is greater than the parent node. So that is followed by the nodes in figure C. That means this AVL tree can be called an AVL search tree. Now look at the last figure, that is figure D. Here it's a binary tree. It also follows the BST concept, but look at the balancing factor values of the nodes. Here some nodes have a balancing factor of 2, that is minus 2 and plus 2 are there. That means this is not an AVL tree. It is a binary search. It can be said as a binary search tree, but it is not an AVL tree. So it is a non-AVL search tree. Now let's see how insertion is performed in an AVL search tree. If after insertion, if the balancing factor of any of the nodes turns out to be anything other than the values 0, 1 or -1, then the tree is said to be unbalanced. So we have to balance it by performing rotations. So there are 4 types of rotations. That is, rotation is a mechanism which shifts some of the subtrees of the unbalanced tree to obtain a balanced tree. There are 4 different types of rotations in AVL. The first one is LL rotation, second one is LR rotation, third one is RR rotation, and the last one is RL rotation. Now let's see LL rotation. So LL rotation is performed when a node U is inserted in the left subtree of the left subtree of A. That is, LL rotation is performed when a node U is inserted in the left subtree of the left subtree of A. Now consider the example. Here you can see a tree where the root node is A. It has a left subtree where you have a node B, and it has a left subtree BL and a right subtree BR. And A also has a right subtree AR with height H. Here the heights of BL and BR are H each. The balancing factors are given within brackets for each node. Now look at this node. Now it's a balanced tree. The heights are balanced. Since the balancing factors of the nodes are 0 and 1, it is a balanced AVL tree. Now suppose we are going to insert a new node U to the left of the left subtree. So left of the left subtree of A, I am going to insert a new node, say U. So once I have inserted a new node U, the height of the left subtree is increased by 1. That is, the height of the left subtree of B will be increased to H plus 1, where the height of the right subtree is still H. That means the balancing factor of B has now changed. So we have to check whether the balancing factors of the nodes have been changed and whether it has become unbalanced after the insertion of the new node U. Now the balancing factor of B becomes H plus 1 minus H, that is 1. That is how we get 1 here. And the balancing factor of A becomes, till here it is H plus 1 and we have one more H here. That is, the left side of A, the height of the left side of A has become H plus 2 and the height of the right side of A is H. That means H plus 2 minus H, which will give us 2. That is how we get a 2 for balancing, 2 as a balancing factor of A. Now you can see that since we have one node with the balancing factor 2, the tree has become unbalanced. So we have to perform rotation to balance this AVL tree. Now here, since the new node is inserted to the left of the left subtree of A, we have to perform LL rotation. So the LL rotation will be performed like this. That is, if you are inserted a new node to the left of the left subtree of a subtree, then you have to rotate the tree to the right. So for LL rotation, we are actually making a rotation to the right. That is, just consider that we are just pulling one node to the right. That is, this A will be shifted to the right and B will come on top. That is, B becomes the root and A will go to the right side of B. Now let's see how insertion is performed in an AVL search tree. If after insertion, if the balancing factor of any of the nodes turns out to be anything other than the values 0, 1 or -1, then the tree is said to be unbalanced. So we have to balance it by performing rotations. So there are 4 types of rotations. That is, rotation is a mechanism which shifts some of the subtrees of the unbalanced tree to obtain a balanced tree. There are 4 different types of rotations in AVL. The first one is LL rotation, second one is LR rotation, third one is RR rotation, and the last one is RL rotation. Now let's see LL rotation. So LL rotation is performed when a node U is inserted in the left subtree of the left subtree of A. That is, LL rotation is performed when a node U is inserted in the left subtree of the left subtree of A. Now consider the example. Here you can see a tree where the root node is A. It has a left subtree where you have a node B, and it has a left subtree BL and a right subtree BR. And A also has a right subtree AR with height H. Here the heights of BL and BR are H each. The balancing factors are given within brackets for each node. Now look at this node. Now it's a balanced tree. The heights are balanced. Since the balancing factors of the nodes are 0 and 1, it is a balanced AVL tree. Now suppose we are going to insert a new node U to the left of the left subtree. So left of the left subtree of A, I am going to insert a new node, say U. So once I have inserted a new node U, the height of the left subtree is increased by 1. That is, the height of the left subtree of B will be increased to H plus 1, where the height of the right subtree is still H. That means the balancing factor of B has now changed. So we have to check whether the balancing factors of the nodes have been changed and whether it has become unbalanced after the insertion of the new node U. Now the balancing factor of B becomes H plus 1 minus H, that is 1. That is how we get 1 here. And the balancing factor of A becomes, till here it is H plus 1 and we have one more H here. That is, the left side of A, the height of the left side of A has become H plus 2 and the height of the right side of A is H. That means H plus 2 minus H, which will give us 2. That is how we get a 2 for balancing, 2 as a balancing factor of A. Now you can see that since we have one node with the balancing factor 2, the tree has become unbalanced. So we have to perform rotation to balance this AVL tree. Now here, since the new node is inserted to the left of the left subtree of A, we have to perform LL rotation. So the LL rotation will be performed like this. That is, if you are inserted a new node to the left of the left subtree of a subtree, then you have to rotate the tree to the right. So for LL rotation, we are actually making a rotation to the right. That is, just consider that we are just pulling one node to the right. That is, this A will be shifted to the right and B will come on top. That is, B becomes the root and A will go to the right side of B. That is, while pulling this A to the right, B comes on top and the A along with its subtrees come to the right of B. So here A along with its subtrees means A has only a right subtree, so that will also come along with A. Now when B has become the root, the left side of B will be as such. That is, you have a subtree BL along with the new node U. Okay, now we can see that the subtree BR doesn't have a place to be accommodated with B. So the only space vacant here is the left side of A. So BR will be attached to the left of A. BR comes here. This is how we get this figure. So this is LL rotation. That is, LL rotation means you are inserting a new node to the left of the left subtree of A, and at that time we have to rotate to the right. That is, just pull one node to the right and note all the changes and adjust the subtrees accordingly. Now after rotation, you can see that the balancing factors of the nodes have changed to 0, since in the case of A, you can see that the left and right subtrees are of height h. That means the balancing factor is 0. And for B, here it is h plus 1. Here this h plus this 1h will make it h plus 1. So here also the balancing factor of B is 0. Now let's see an example for this, for LL rotation. Now look at this figure. Now in this figure we are going to insert a node C to the left of the left subtree, right? So C is inserted to the left of D. Now let's calculate the balancing factors for each node. As C is the leaf node, you can see that the height of C will be, the balancing factor of C is 0, since it does not have a left and right subtree. Now the balancing factor of D will be, it has the height to the left is 1 and to the right is 0. So D has a balancing factor of 1. Now the height of F. Here to the left there are two edges, that is, a height of left subtree of F is 2 and the height of right is 1. So 2 minus 1, it is 1. And balancing factor of K is 0, since it does not have any subtrees. The same is for S, since it does not have the subtrees. Now in the case of M, the left subtree of M is 1, 2, 3. This is the height. So 3 is the height of the left subtree of M. So 3 minus 1 will give you 2. Now it becomes an unbalanced AVL tree. Now to make it balanced, since the insertion was to the left of left subtree, so we have to perform this rotation, that is LL rotation. That means you have to shift to the right, just pull one node to the right from the root. So pulling, you can see that this M along with S comes to the right of F. When you pull this M to the right, this F will be lifted to the top, right? So F comes, now F becomes the root and M will be shifted to the right along with its subtree, that is S. Then F has become the root. The left subtree of F should be drawn as such. And now we have to draw K, which was actually to the right of F. Now since F already has a right subtree, the space vacant is here, that is, you have to insert it here. That's how we have done in LL rotation. This BR will become the left subtree of A. So here A was M, so K will become will be attached to the left of M. Now find the balancing factor for each node. Here the leaf nodes will have a balancing factor of 0. Then M will have a balancing factor of 1. Then M will have a balancing factor of 0, since both sides are 1. Then D, 1 minus 0. So 1. Here 2. Here also height is 2. That means F will be having a balancing factor of 0. Now it is a balanced AVL tree. The second type of rotation is LR rotation. LR rotation is performed when a node U is inserted in the right subtree of the left subtree of A. Now look at the first, look at the tree here. Now this is the tree. Here it is an AVL tree, since the balancing factors are 1 and 0. So this can be considered as an AVL tree. Now you are going to insert a node U to the right subtree of the left subtree of A. Okay, right subtree of the left subtree of A. So U is inserted here. Now when U is inserted, the left subtree of C will have a height of h, and the right subtree is at height h minus 1. So the balancing factor of C will become h minus of h minus 1, that is 1. Now in the case of B, the balancing factor is the left side of B is at height h, and the right side we have a height h to the left of C. So till here we have h, and then plus 1 we will get h plus 1, since this is the longest path of the right subtree of B. So the height of right subtree of B is h plus 1, and the left side is h. So h minus of h plus 1 will give us minus 1. Now look at the balancing factor of A. Here the longest path is, this is the longest path. So the height of the longest path is h plus 1 plus 1, that is h plus 2. So h plus 2 minus h will give us 2. Now the AVL tree has become unbalanced, that is after inserting U, where the AVL tree has become unbalanced. Now we have to balance it. So since U was inserted to the right subtree of the left subtree of A, we have to perform LR rotation. So the LR rotation is performed like this. So LR means we have to rotate to the right. Okay. So for LL and LR we will be rotating to the right. But since the insertion was to the right of the left subtree of A, so there's a change in the rotation, that is this C now becomes the root node. Okay, only then it will become it will still be an AVL tree. Okay, so for LR rotation, since we have a node C and the new node was attached as a child from to the subtree of C, so we have to make C as the root, only then it will be balanced. So to balance the tree, we have to make the C as the root. So the C becomes the root. The left of C will hold the B, and the right of C will hold A. That is, actually this A is pulled to the right, but B cannot be made as the root. Only C can be made as the root. Only then this tree will be balanced. So for LR rotation, you have to make the C as the root, put B to the left and A to the right of C. Now the child nodes of C, that is the subtrees of C, that is CL and CR, will be attached to the B and A, to the vacant spaces in B and A. Since A is shifted to the right, this A along with its subtree will be shifted to the right. Okay, so the left side of A will be vacant. Now in the case of B, since C was put on top and the B was just kept as such, so the left side of B will be as such and it will not be disturbed. So the left will be as what it was before, but the child nodes of C will have to be split to these two. That is, the left subtree of C will be attached to B and the right will be attached to A. So this is how the tree becomes after LR rotation. Now the tree has become a balanced tree. If you check the balancing factors for each node, you can see that the balancing factors are 0 or minus 1, right? So now it has become a balanced tree. So to make an LR rotation, you have to make the C node as the root. Now let's see this with the help of an example. Now consider this example. This is the tree which we have here. This green colored one stands for A, yellow for B, and this orange for C. Okay, now a new node H was attached to this tree. It is attached to the right subtree of the left subtree of A. Here A is S. So H is attached here. Now the balancing factors have changed and it has become an unbalanced AVL tree. So after performing LR, what will happen? We have to make this orange color, that is what is the node which represents C, right? So this has to be the root. So L will be kept as the root. Then this S along with W will go to the right side of L. this F along with its left child will go to the left of L, and now this we have to insert H. Since H is the left child of L, it has to be attached to the right of B. This is how the AVL tree after LR rotation, the balanced AVL tree will look like. The third rotation is RR rotation. Here a node U is inserted in the right subtree of the right subtree of A. So RR means RR rotation takes place when a node U is inserted in the right subtree of the right subtree of A. So look at this figure. This is the sample one. So here we have a node A and another node B with their child, with their subtrees. Okay. Now if a new node U is inserted to the right subtree of the right subtree of A, what will happen? We have to perform RR rotation, and let's see how this RR rotation is performed. So we are going to insert U to the end of BR, the subtree BR. So U is inserted here. Now the height of BR has become H plus 1. Okay, when the height of BR has increased, the balancing factors will change. So now the balancing factor of B has become H minus of H plus 1, that is minus 1, and the balancing factor of A will become H minus, this right side of A will have a height, till here it is H plus 1 plus 1 more H, right? So H plus 2. So H minus of H plus 2, which will give us minus 2. Now this has become an unbalanced AVL tree, and it has to be balanced by RR rotation. So the RR rotation will rotate the tree by one node to the left. So RR will rotate to the left, to the opposite direction, right? So it will be rotating to the left. So it will go like this. That means A will be shifted to the left side and B will go up. So B becomes the root and A will be shifted to the left. So A along with its left child will go to the left side. Now when B was shifted to top, what happens? B will become the root and the right subtree of B will be like that, and we have to give space for BL now. So BL will be attached to the left of A, the right of A. Okay, so we just shifted the A to the left side. Just pulled the A to the left. So when A was pulled to the left, B took its place, and so the rest of the subtrees have been rearranged like this. So this is how an RR rotation is performed. Now with the help of an example, let's see what happens. This is the tree which we have here. A new node has to be attached to this tree. Now as you can see, looking at this tree, you can see that the node A in this example is K, the node B in this example is T. So a new node will be, if we attach a new node to Y, we have to perform RR rotation. Now the nodes have been colored according to the above colors based on the above figure. That is, here A, the node K indicates A and T indicates B, right? Okay, now I'm going to insert a new node to the right of Y. Say Z. I'm going to insert Z to the right of Y. So this is the new node that we have inserted. Now let's see what the balancing factors of each node. Let's calculate the balancing factors once again, so that we can know if it has become unbalanced or not. Now the balancing factor of Z is 0, since it does not have a left and right child. Now the balancing factor of Y becomes, since it does not have a left one, the height of left side is 0 and the height of right is 1. So it has changed to -1. Now the balancing factor of T, 1 minus 1 plus 1, 2. So 1 minus 2 it also becomes -1. Now the balancing factor of k. The left side of k has a height 1 and the right side 1, 2, 3. Take the height of the longest path. So 1, 2, 3. So 1 minus 3, it becomes -2. Now the tree has become unbalanced since we have a -2 here. So to make it balanced, we have to perform RR rotation. So RR rotation is performed by rotating to the left side. That is, the k will move to the left and t will take its place, right? So the root now becomes t. To the left, this k will go along with its subtree. Now when t goes up, the right side of t also goes along with it. So okay, now the leftover is n. N should be placed to the, n will shift to the left subtree, right? So that is to the right of k. See, this BL goes to the right of A. Here A is k. So BL will be the right subtree of k. Now this is how the rotation is performed. Now we have to check the balancing factors of each node here also. The balancing factor of E is 0 since it does not have a left and right subtree. The same is the case for N and Z. Now the balancing factor of K is 1 minus 1, which is also 0. Now for Y it is 0 minus 1, that is -1. Now the balancing factor of T. Left side we have a height 1 plus 1 2 and the right side also 1 plus 1 2. That means balancing factor of T is 0. Now it has become an AVL tree. The fourth type of rotation is RL rotation. That is, RL rotation is performed when a node U is inserted in the left subtree of the right subtree of A. That is, when U is inserted in the left subtree of the right subtree of R. So if this is the tree, then when U is inserted to the left subtree of the right subtree of A. Left of the right of A. So U will be inserted to either CL or CR. Now after insertion of U, you can see that U is inserted. This is the node U, which is inserted to the left of the right of A. Okay, right subtree of A. So U is inserted here. Now the height of CR becomes H, and when we check the balancing factors of each node, we can see that the balancing factor of C has become H minus 1 minus H, which is -1. Now for B, it is the longest path of B, longest path to the left of B is this, that is 1 plus H, that is H plus 1. So the height of the left subtree of B is H plus 1 and the height of the right subtree is H. So H plus 1 minus H becomes 1. Now in the case of A, the left of A is at height H and the right side take the longest part. So 1 plus H. The fourth type of rotation is RL rotation. That is, RL rotation is performed when a node U is inserted in the left subtree of the right subtree of A. That is, when U is inserted in the left subtree of the right subtree of R. So if this is the tree, then when U is inserted to the left subtree of the right subtree of A. Left of the right of A. So U will be inserted to either CL or CR. Now after insertion of U, you can see that U is inserted. This is the node U, which is inserted to the left of the right of A. Okay, right subtree of A. So U is inserted here. Now the height of CR becomes H, and when we check the balancing factors of each node, we can see that the balancing factor of C has become H minus 1 minus H, which is minus 1. Now for B, it is the longest path of B, longest path to the left of B is this, that is 1 plus H, that is H plus 1. So the height of the left subtree of B is H plus 1 and the height of the right subtree is H. So H plus 1 minus H becomes 1. Now in the case of A, the left of A is at height H and the right side take the longest part. So 1 plus H, that is H plus 2. Now the balancing factor of A is H minus of H plus 2, which is minus 2. Now the tree has become unbalanced, so we have to perform RL rotation to make it balanced. Now the RL rotation is performed by shifting this C to the root. So C becomes the root here and A will be shifted to the left of C. So C becomes the root and the node A along with its subtree will be shifted to the left of C, and B and its subtree will be to the right of C. Now the subtrees of C will be shifted to either sides of the tree, that is CL will be shifted to the left and CR will be shifted to the right. That means CL becomes the right child of A and CR becomes the left child of B. Now the tree has become a balanced AVL tree. Now this can be illustrated with the help of an example. So consider the tree here. The balancing factors are given in brackets and you can see that this is an AVL tree. It is balanced. Now we have to perform RL rotation after inserting a node to the left of the right subtree of this G. Okay. So I am going to insert a new node to the left of the right subtree of G. That is, I am going to insert a node M to the right of K. Okay. Now let's see the balancing factors. The balancing factors of each node after the insertion of the node M is as such. Now you can see that we have one node with the balancing factor minus 2. That means now the AVL tree has become unbalanced. Now to make it balanced, we have to perform RL rotation. So RL rotation means we have to shift this G to the left, and since the new node was inserted to the left of the right subtree of G, so we have to make this K the root here. So in the balanced tree, K will become the root. Then this G will be shifted to the left along with its subtree, and now to the right of K we have T along with its right subtree, and the remaining what we have to insert is this M, which will be shifted to the right. That is, here also you can see that when C became the root, left of C was attached to A and right of C was attached to to B, that is to the right subtree, and left was given to the left subtree. So here, since M is to the right, that means M will be attached to the right subtree. So M will come here. Now looking at the balancing factors, we know that the leaf nodes have a balancing factor 0. Now in the case of T, 1 minus 1 is 0. Here for G, 1 minus 0 is 1. And for K, 1 plus 1, 2. That is, left side the height is 2 and then to the right also the height is 2. That means the balancing factor will be 0. Now this is how the tree looks after balancing. After performing RL rotation, we have a balanced AVL tree here.